Hey everybody, this is Mr. Beckstrom, and today we're going to go over mathematical models. This is from 2.6. This is going to be one of the harder topics that we cover, so I'm not expecting everyone to completely understand right away. This is going to take some practice. It's going to take some reading, trying different types of problems in order to really start to cement these concepts here. But here we go. So what's going to happen is you're probably going to receive some type of instructions, and they're going to ask you to minimize or maximize something, either make it as large as possible or as small as possible. So once they do that, the first thing we want to do is just kind of draw a picture to try to see what they're asking us to do, or sometimes one will be given to you. We want to determine the quantity to be maximized or minimized. For example, we might be maximizing the volume of a box, or maybe we're minimizing the cost of producing an item. So there's lots of different types of equations that we can be using. Then we want to find what's called the constraint equation. And that's the equation that is going to help us get the optimization equation, the min or max equation, into terms of just one variable. Sometimes it'll already be in terms of one variable, but sometimes we need something else in order to help us convert it. Then we're going to use those strengths again to substitute into our maximum minimum equation, so it can be written in terms of only one variable. So for example, if we're looking for the volume of a box, we want all of the variables just to be probably x or t or some single variable. We don't want to be dealing with an x, a y, and a z when we're talking about a volume. And then we want to graph that equation. This is the optimization equation, and choose an appropriate window, and then we're going to find the minimum or maximum point using our calculator. So if you can, go ahead and pause the video at this point and take some notes and write down these steps because we're going to be using those. Okay, so let's up and finally state the answer to the problem and include the correct units. The easiest way to do units at the end is if you're talking about a distance, that's going to be a unit to the first degree. So that would be something like centimeters or miles. If it's an area, if it's an area of something like the area of a square, area of a circle, your units are going to be squared. So it could be centimeters squared, or again, miles squared. And if it's volume, a three-dimensional space at the end, then you either want to use the cubic version, or you can, if the word itself encapsulates that third dimension, such as a pint, for example, then you can keep that in the first power, but anything else would be the third. So it'd be centimeters cubed, it'd be miles cubed, it'd be seconds cubed, things like that. All right. So here we go. It says a topless box will be constructed from a piece of cardboard 20 inches by 12 inches long. What size should the corner empty spaces be to get the maximum volume of the box? So just looking at that, yes, it looks pretty tricky, a little complicated, not quite sure what they're asking, but let's just start to draw a picture of this. So, and so I'm going to go to my whiteboard here. So we have a piece of cardboard. And again, it said it is 20 inches by 12 inches. So let's go ahead and oops, call this sorry, right here. This here will be the 20 inches, and this side here will be the 12 inches. 12 inches. Okay. Now, what we want to do is we want to take that flat piece of cardboard and we want to cut boxes or squares out of the corners in order to be able to fold it up to make a three-dimensional box. So let's go ahead and go back here, and we're going to draw just kind of a square in each corner here. Kind of get an idea of what we're talking about. So square there, square here. This is cutting out a square in the corner. And I know it's not perfect, but hopefully we can get a good idea of what we're looking at. So we're going to be cutting out a square, and then we're going to be folding up the sides and then folding up these sides to make a three-dimensional box. And we want to know how large should these squares be, and they all need to be the same size in order to maximize that three-dimensional space in this box we're going to create. So again, once we cut those out, we are going to fold along these dotted lines here. So let me so that way we can maybe better picture this. Okay, and finally here. All right, so cut the squares out. So these parts will not be in there. And then we're going to fold up the other four sides to make that box. All right, so let's go ahead and start labeling this and in terms of one variable if we can. So for example, for the box, remember the squares have the same side as they do the length. So since we don't know how large these squares that we're going to cut out are, let's just call this side here X, and we could call this Y, but since it has to be the same as this side, we'll call that X as well. And we're going to do that for each one of these boxes. Excuse my horrible X's. All right, so there, here, and here. Okay, so remember, we're trying to find the volume of this box. So we do need to know what the volume of a rectangular prism is. And if you don't know, it is length times width times height. Length times width times height. All right, so let's think of this side here. We'll call this the length. So this is our length is equal to 20 inches. So far, our width will be this side here. So we'll call that our width. And then our height will be the portion here that we fold up. So in this case, our height is going to equal just X, right? Because once we fold this box up, then this part here will just be the height. All right, so we have these three. So I can already go to my volume here, and I can replace the H with X. So this is going to be length times width times X. And right now what I'm trying to do is I'm trying to get all of these variables in terms of X. Okay, so we have the height, which we just replaced it over here. Now let's look at the length. What is the length of the final box going to be? Well, it's going to be 20 inches minus this X, because we're cutting that part out, and minus this X. So it's going to be 20 minus X minus X. So our length is actually going to be 20 minus 2X. All right. And then how about our width here? Well, that's 12 inches minus this X minus this X. So we're going to have the same kind of thing over there as well. So the width is going to be equal to 12 minus X, which is just 12 minus 2X. Now we can replace the L and the W with 20 minus 2X and 12 minus 2X. So our volume is going to be equal to our length, which is 20 minus 2X. Sorry. And then times our width, which is 12 minus 2X. So 12 minus 2X times our height, which is just X. Okay, so this is pretty hard to get to, but we finally got our equation in terms of one variable. Now, as far as your calculator, you could leave it just like that, and it would be fine. But let's go ahead and go back to our picture. So again, we're going to draw that diagram just like we did. And this is pretty much how we set it up here. And we want to get something that looks like this in the end. All right, so again, we're using the formula for volume. That's what we're going to optimize. In this case, that's what we're going to maximize, not minimize. We found this equation by replacing h with x, w with our width with 12 minus 2x, and our length with 20 minus 2x. You can clean that up if you want to by kind of multiplying everything together, or you can just leave it like that. And I'm just going to leave it like this up here just to make it easier for my calculator. And we know that the width has to be somewhere between 0 and 6 inches. So this would be a constraint here. Why does it have to be between 0 and 6? Because the entire width is 12 inches. And we know that it can't be more than half of that, each one of those x values that we take out. All right, so now we're going to pull out our calculator and try to graph this and find the maximum point. Okay, so we're going to go to our y equals here. Clear any functions you have there. And this was x times 20 minus 2x times 12 minus 2x. 12 minus 2x. Now, we might have a little bit of issues trying to find a window that's going to show this maximum, so we might need to do a little bit of trial and error. But this is our equation here. So like we normally do, let's go ahead and start with a zoom 6, which is our standard. And yeah, this is way off. Now, if it's way off, we can't see that that maximum value up here. We know we have to extend the y window pretty large. We can go to our window and just keep trying values until we get it. But there's a couple other things we can try too. So one thing I might try to do is do a zoom fit. Sometimes that'll work, sometimes that won't. It depends on the equation. Let's give that a try. And technically here, I can see where that highest point is. So yeah, we can find it from there, but let's go back to the zoom 6 and really try to get a good view of this local maximum. So if I go to my window here and I know I want to increase my y values, let's start with like 100. Right now it's at 10. Let's go up to 100 and see if that includes it. Oh, looks like we're getting closer to that top. So let's make that y scale even larger. Let's go 200. And if you want to change the scale, you can, so you don't see as many slashes in the axis. So I'll just change that to 100 there. But you don't have to change that. Just we want to change our y max. So, oh, we are close to that top. So maybe one more should do it. So let's change that y max to 300 so we can see that peak. And there it is. There it is. That's what we want to see. Remember, we're trying to maximize our x value, right? So the maximum x value is going to be where this peak occurs. So we're going to use our calculate menu, so second trace. We're going to try to find that maximum. Now we want to keep that maximum between two different bounds, so we know we're looking for this one here. So it says first do a left bound, so just anywhere on the left side of that peak. I'm going to hit enter, and then it asks for a right bound, so I'll go to the right side of that peak with a little arrow thing and hit enter. And so now it knows it wants to find the x value and y value, where the y value is the highest here. All right. Hit enter one more time, and here it is. So x is going to be about 2.43 inches, and that will give us a maximum y value, which remember in this case is the volume of about 262.68. And let's look back at that unit. Did they give us units for this one? Inches. So this would be a volume of that many, or inches cubed. Oops, let's go back over here. And this is what the window will look like. So we went up to a Y max of 300 to get that in there. And we did the maximum function here in our calculator, and we got this value. So to answer that, we would say we would need to cut out squares in the corners with a length of 2.43 centimeters, length and width of those squares of 2.43 centimeters, and that will maximize our volume at 262.68 cubic centimeters, or excuse me, inches cubed. All right. There we go. So if you have any other questions, please let me know. And I did put a couple of these types of problems on the quiz, so I'll be going over a couple of more examples this week. All right. Thank you, and have a great rest of your week.